be going over the first and second derivative tests. So, the first and second derivative tests are used when you want to know the critical points, slope, point of inflection, etc. of a function when you are not given the graph of that function. So, let's say it says, let f of x equals 2x cubed minus 8x squared. Now, let's see what it asks. It asks, find all intervals from -2 to 2 where the slope is increasing. Well, find the slopes, you'll have to find the critical points, and basically critical points are the highest or lowest points of a graph, and with those you can get slope. So to find critical points, you have to derive and solve for x. I'll show you here. So derive the function 6x squared minus 16x. Now I'll have to solve for x, and to solve for x, you'll have to use zero product property and whatnot. So, simplifying it, 2x, 3x minus 8. So with zero product property, x equals 0, and 3x equals 8. Cancel out 3, and x equals 8 over 3. And these are our critical points. Now that we found our critical points, we can plug this into a number line. That'll show us whether or not the slope in between these points are increasing or decreasing. And that's where the first derivative test comes in. So let me erase this. Now we represent it using f derivative of x. And we'll put a point here that says 0, and a point here that says 8 over 3. That's an 8. And that's a 3. Wonder why I put the derivative of x? Well, we'll be plugging that in to this number line into points before 0 and in between and after 8 over 3. And 8 over 3 is roughly 2. So I'll go with 3 here, 1 here, and -1 here. Now, the derivative of this function is, remember, it's 6x squared minus 16x. So we'll have to plug in -1 into this function. That'll be 6, 1, because, you know, the squared, negative number squared is always positive, minus 16 times -1, and that will give you a positive. And that means we get 6 plus 16, which equals 22. And 22 is positive. You'll have to check whether the number is positive or negative to see if the slope is positive or negative. And since this number 22 is positive, all the slope from -1 to 0 is positive. Now, we'll keep doing this. Now we'll plug in 1. 6 1 squared is 1, and negative 16 times 1 is negative 16. And negative 16 plus 6 is 0. Is 10, sorry. Negative 10. And negative 10 is negative, so all the slope from 0 all the way to 8 over 3 is negative, and you'd write it like that. And now, to determine whether, well, actually this should be pretty obvious, but we'll prove it anyway. Minus 16 times 3. Well, 3 squared is 9 times 6 minus 16 times 3. Now, which one's greater? 9 times 6 or 16 times 3? Well, I did the math already, and I determined that 6 times 9 is actually greater. It will give you 72. 60 times 3 will not give you anything close. 54. And negative 16 times 3 is not anything of greater value than 54. So it's positive. There you have it. Now, if I were to graph this, it would look something like this. Let me see. There's your big, rough graph. And it will look like this. From here it'll be like this. Then from here it'll be like this. And so on. Not exactly, but roughly. Yeah, that's the first derivative test. Now for the second derivative test. For the second derivative test, it's basically the same thing, except instead of slope, we're looking for concavity. Whether or not a curve is going up, as in like this, or that's down, or up, down, up. To figure this out, we'll do basically the same thing again, and I'll use the same problem, the same function I used before. If we wanted to figure out whether the concavity between negative 2 and 2 went up or down, we'll have to plug f. We'll have to use that derivative this time. F derivative of x equals 6x squared minus 16x. We'll have to derive that again. You'll understand why once I get to it. So 12, whoops, 12x minus 16. And from here, we do the same thing. We figure out a critical point, and it looks like it's 12x equals 16, 12. So it's 16 over 12. I think we could simplify that a bit. X equals 3/4. 4 over 3, basically. 4 over 3. And now, plug that into the second derivative number line. With 4 over 3 being our only point, since it's our only point of inflection. And we plug it into our second derivative. So 12x minus 16. 4 over 3 is roughly somewhere between 2 and 1. So this time I'll use 1 and 2 to figure out whether the concavity was going up or down in between this point. Well, between these 2 points. We'll find one, we'll find the other. So 12x minus 16. So 12 minus 16, that's negative, so this is going to be negative. And 24 minus 16, that's positive, so here it is. It was a negative concavity before it reached 4 over 3, and a positive concavity after. And the way you would show this is basically like this. Here's my graph. I'll just erase this too. Here's my graph. Here's my y-axis and my x-axis. And 4 over 3. So it was a negative concavity before it reached 4 over 3. So it was basically like this. And then when it reached 4 over 3, it turned to a positive concavity. So like that, basically. And that's our second derivative test. And that in all is the first and second derivative tests. That wasn't too long. Signing out.